Okay, so today's lesson is lesson 4, and the title is on the previous page, so I just drew it in there. We're going to look at solving problems with exponential equations. So the first thing that we actually need to look at is what an exponential equation or an exponential function looks like, and how we see those on a graph and what that actually means. So an exponential function is written in the form y equals a times x, or a times b to the x. So b to the x here is my power, right? And the key thing about an exponential function is that variable has to be in the exponent. Okay, so it's different than something like y equals x squared, because y equals x squared, the variable is not my exponent. This is just a parabola. Okay, so my x is in my exponent, so that's what makes it different. B for this class is going to be greater than 0, and it's not going to be equal to 1. Okay, so it's going to be positive and it's not going to be equal to 1. So exponential functions model either rapid growth or decay. Okay, so there's lots of things that grow exponentially. Investments are one, or the value of a car depreciates exponentially, right? As soon as you drive your car off the lot, it starts decreasing and then it kind of levels out. Okay, or maybe there's something about, I don't know, a population of something and it grows exponentially because things are reproducing quicker than they're dying. It's the human population. Okay, so that's kind of what those look like. So decay or growth. Okay, so we're going to kind of look at one of each of these graphically and see some kind of things about them, some patterns about them, and just kind of see what they look like. So if we want to pick a b value that's bigger than 1, basically that means that we're going to have a growth function. So b is kind of like our multiplier. It's what this thing is being multiplied by over and over and over again. So let's say b is 2, and that is getting multiplied every time x increases. And then a, let's just pick a random number. So let's make our exponential function 3 times 2 to the x. So I'm going to actually graph that. Oops. 3 times 2 to the exponent x is my function, and I'm going to graph it. So notice how we've got that exponential growth, right? The slope is smaller down here than it is up here. It gets steeper and steeper and steeper as we go. So we're just going to sketch ourselves a little picture there of what this thing looks like. Kind of looks like that. Okay, so in this equation that we picked, okay, our a value is 3, okay? And what that's going to represent is our starting point. We'll get to that in a second. Our b value is 2, okay, which basically means it's our multiplier. It keeps getting multiplied, so every time x goes up by 1, it doubles. Up by 1, the y value is going to double. So over and over and over again, that's going to happen. So a b value of 2 is kind of like it doubling. Our x-intercept, so that's where it touches the x-axis, there's actually not any, because if we go to the right, things are doubling. If we go to the left, they're halving. And no matter how small the number gets, you keep dividing it by 2, it's just going to keep dividing by 2. It's never actually going to be 0 as long as you don't round. So there's actually no x-intercept. For a y-intercept, I can do this on my graph. So I can go, there's a few different ways to do it. So if I go second calc, and just I want to know the y value at a particular value of x, so I'm going to hit number 1. And I'm going to just say, okay, when x is equal to 0, that's going to be on that y-axis. Give me the y value. So that's 3. So if we remember, so I said 3 is like our starting point. So right when x is equal to 0, y is equal to 3 right there. So that a value is kind of like our starting point. We're going to use that a whole bunch as we continue. Okay. The domain is x is an element of all real numbers because it goes left and right infinitely. And then my range is y has to be greater than 0 because it doesn't actually touch that y-axis and it goes all the way up to infinity. Okay, so that's what a growth function looks like. If we want to do a decay function, so we're going to choose a b value between 0 and 1. Okay, so we talked about how every time if we multiply by 2, it's like a doubling. If I make my b value 1/2 and I put my x on that guy, and then let's just say my a value is 4, something like that, that means every time we go up an x, every time we like go one to the right on this graph, my y value is going to be multiplied by 1/2, which is the same thing as dividing by 2. So this one basically is going to be half of what it was every time. Okay, so again, we're going to graph this. So clear that one. We're going to go 4 times 1/2 to the x and graph it. And so there's my function. So it looks kind of like that. Okay, so a decay function, instead of growing as we go to the right, which is how we would read a graph, right, like left to right, it's shrinking, it's decaying, there's less of it. Okay, so my a value this time was 4. My b value was 1/2. So we can talk about that like it was, I guess, halving. Halving is not a thing. Halves should be spelled with a V. So it's like that thing is halving in every time, right? Getting cut in half. My x-intercept, again, there's none. My y-intercept is going to be that initial value. So just how like my a value and my y-intercept matched here, my a value is going to match my y-intercept there. Okay, so you could graph this, we could check that, kind of double check it here. So we could also look at the table. So if you go second to the graph button, it's going to give you a table, and so when x is 0, y is 4. So we see that. My domain is x is all real numbers again, and then my range is y is greater than 0. So that's kind of like the standard form of an exponential graph. And so we're going to think about some applications, and I think it's just helpful to have a picture of how that looks as we do some applications. Okay, so when we start talking about applications, there's one equation that we're going to use over and over again. Okay, so it looks like this, and I believe it's given to you on the formula sheet, but I didn't check, but I think it is. So we've got y equals a times b to the t over p. So this looks really similar to what we just did, except for that p. Okay, so this, we have to know some specific meanings for each of these. Okay, so just like on the examples above, the a, the thing that's going to multiply this power, so this whole thing's the power, that a value is always going to be my starting value. Okay, my b, the base of my exponent, is always going to be my growth or my decay rate. And another thing that I like to think of it as is like your multiplier. So for every hour that goes by, or for every, usually it's time, for every hour that passes, it multiplies by 2. So it multiplies by 2. So it would be times 2, times 2, times 2, times 2, times 2, for however many hours you have. And that's where we see that exponent, right? It's 2 times 2 times 2. It's that repetitive multiplication. Okay, so whatever your multiplier is, if it's like doubling or halving or whatever, it's going to look something like that because of that power. My y is my final amount, or my the value that my equation is going to be spitting out, so my final amount. And then t, like I said, is generally time. Okay, and one thing that's important to remember here is that y and t go together. Okay, so if we're looking for the value, the number of rabbits or the number of chicken nuggets or the number of whatever it is, after a certain amount of time, that's the y value and it corresponds to that t. Okay, then the other thing that we have in here is this p value. Okay, and p stands for the period, and it's for the growth rate to happen. Okay, so sometimes it's like it grows every year, and then we would say p is just 1. It happens once per year. Sometimes the period is it happens twice per year. So then the period would be like half of a year. And so you'll see some different applications for that. So just like y and t go together, the other thing that we need to know is that b and p go together. And I kind of remember this by PB is peanut butter. And that's delicious, right? They go together, kind of like peanut butter and jam. There's no jam, but there's peanut butter and they go together, okay? So y and t go together, right? The y corresponds to the time t, and then b and p go together, okay? The other thing that we need to remember is that t and p, so usually these are like application type questions, right? Where they're gonna have like units and stuff. T and p need to have the same units. So like if t is in hours but p is in minutes, we need to convert them to be the same. Okay, so now we're going to do some examples using this guy. So a population of rabbits will double every 6 months. If there's an initial population of 25 rabbits, how many will there be in 3 years? Okay, so we need to read all this information, and I'm going to just write kind of my base equation up there. So y is equal to my starting value times my multiplier to the exponent of t over p, the time and the period that it takes for b to happen. Right, so y and t go together, b and p go together. So a population of rabbits will double every 6 months. That means that my multiplier, or my base, is going to be 2. And the fact that it happens every 6 months, this doubling happens every 6 months, is that p is equal to 6 months. And instead of just putting 6, I'm going to put months just in case my units don't match. If there's an initial population of 25 rabbits, that means that A, my starting point is 25. How many will there be? So how many will there be? We're looking for Y, my end population, in 3 years. That means T is 3 years. Okay, so what I'm going to do is I'm just going to write my equation, A, B, T over P. If you use a capital A or lowercase a, I don't really care. And we're going to plug in what we know. So Y is my unknown. I'm going to leave that as a variable. A is my starting point, so 25. B is my base, or my multiplier, so 2. T is 3. And then P is 6 months, but remember that these two need to match. Okay, so I could have either converted 3 years to months, which is, I don't know, harder in my opinion, than turning that into 0.5 years. Okay, so these two have to match those units. Okay, so now we're just solving. So we're going 25. I'm going to simplify my exponent first. So 3 divided by 0.5. Dividing by 0.5 is kind of like multiplying by 2. You can punch that in your calculator, but we get 2 to the 6. So that's 25 times 64. And that's going to be 1,600. And we're talking about rabbits. So kind of like a unit, we're going to put our thing that we're talking about in our answer. Okay, so that's how that's going to work. Do a few more examples. So A car depreciates, so it loses value at a rate of 5% per year, which is probably actually lower than what it is. It probably loses it faster. If the car was purchased for $32,000, we want to know how much is it going to be worth in 6 years. Okay, so if my car was purchased for $32,000, that means that my initial amount is going to be $32,000. Right? This is the thing that's going to be multiplied over and over and over and start decaying. Okay. If it depreciates, so my T is going to be 6. If it depreciates at a rate of 5% per year, that means that P is actually 1. It takes 1 full year to get that 5% depreciation, or to lose 5% of its value. Okay. Now, to find what B is, so the car started at 100% of its value, and then it's going to lose 5% each year. So that's actually 95% that it retains. And we want to talk about what it retains, because that's what we're going to do. That's what we do as a multiplier, right? So like if I said something was like 25% off, I'm just going to draw up here. So if I said 25% off, that means you're still paying 75% of the price. So you'd take the price, let's say it's like $40, and you'd multiply it by 0.75 to figure out what you're paying. Right? So what's left of the thing is what you actually want to multiply by. So this 95% is what's left. Okay, so we could also do this as 1 subtract 0.05, and we could do it as 0.95, because that's what we're going to multiply by, right? Like if we're multiplying by a percent, we always convert it to a decimal. And so it's 100% minus that 5%, and we get 0.95, which is that 95%, and that's what it's going to retain every year. Okay, so it's going to be 95% of what it was, so we have to multiply that. Okay, so that is my B value. So I'm going to write out my formula. Oops, I always write A equals. So it's Y equals AB to the T over P. So Y is the thing that we're looking for, right? How much? Y is our question mark. Our initial value was 32,000. B is 0.95. T is 6, and P is 1. Okay, so what's going to happen is we're going to take that 32,000 and we're going to multiply it by 0.95. It's going to be a smaller number. We're going to do that 6 times. So 32,000, and then 0.95 to the 6th exponent is 0.735 ... but I kept it in my calculator and then multiplied it with all its decimal places to get 23,522 and 94 cents. I'm going to put that as a dollar sign, and because it's dollar, we're going to round to 2 decimal points, because that's how we do money. Okay, so this next question is a little bit different. So when is the car worth half of its original value? So half of its original value is at $32,000 divided by 2. So that would be $16,000. So that's going to be our Y value, right? That's what it's worth. So we're going to plug $16,000. Let's start with the base equation, because that's just a good habit. So Y is 16,000. A, my original price, my original value is 32,000. B is still 0.95. And when is the car worth? That's asking about T. So T is my question mark. So T is my question mark, and P is still 1. Okay, so now we want to solve for something that's in the exponent. So you're probably like, why the heck did we have to do logs, and how does this relate? So in the last lesson, we looked at how do we solve things when our variable is in the exponent, and we had to use logs to get that variable out of the exponent so we could figure out what it was. So that's why we had to do that first, and now we're doing this. So to solve for t, the first thing that we want to do is get just that power, so the base and the exponent, alone on one side of the equation if we can. So what we can do is we can divide both sides by 32,000. They're going to cancel here. And then 16,000 divided by 32,000 reduces to 0.5 or 1/2, doesn't matter. And then what we have left is 0.95 to the t, because t divided by 1 is just t. Okay. So now we need to figure out how to get that t by itself, right? So in the last lesson, we talked about, okay, if we have an exponent like this, one of the things that we can do is try and get the bases the same. But those are both ugly numbers. I don't want to think about that, okay? So the other thing that we talked about is logging it, okay? So since we've got one exponent and then it's equal to something, right? One kind of power, one exponent, and it's equal to something without an exponent, we're going to change this to log form. So change to log form. Okay, so remember that log base 2 of 8 is equal to 3, because we're asking what exponent do I have to raise the 2 to get to 8? 2 to the 3 equals 8. And then, so that's 2 to the 3 equals 8. So you can kind of write that to give yourself a guide of what goes where. And we're going to use that to convert this to log form. Okay, so the base of the exponent stays the base of the log. So it's going to be log of 0.9, log base 0.95. And then what this thing is equal to, the exponential form is equal to, is going to go as the argument of the log, what we are logging. So it's going to be 0.5, and then the exponent is what is the log equal to, right? So now we just have t is equal to log of 0.95, or log base 0.95 of 0.5. And that's something that you can stick into your calculator. So if you have, so enter in calc. So if you have the calculator function that will let you choose your log base, so if you can get it into log base and put stuff in those boxes, you can fill those in. Or if you don't, you're going to have to use the change of base formula. So we're going to change it to log base 10 so we can stick it in our calculators. So it's log base 10 of the argument, the thing in the log, divided by log base 10 of the base. And so either, again, my calculator is too old, I can't do this, I haven't updated my software, so if I do log of 0.5 divided by log of 0.95, and make sure you're closing your brackets there, this is going to be 13.5, so 13.5 years. Okay, so what it means is it takes that car 13.5 years to get to, like if this is the 32,000, this is 16,000, this distance here would be like 13.5 years. Okay, so that's what that means. That's what that looks like. So this is like pretty applicable math. This example, we've got tons of space because there's a lot of things that we need to think about. So a radioactive substance has a half-life of 12 minutes. How long will it take until there's 10% of the substance remaining? So a lot of radioactive things just decay naturally, right? They start dying, and a lot of them have what we call this half-life. So I know some of you have taken chem, and so you might have seen that before. Basically, half-life is the time it takes for half of it to disappear, half of it to die, okay? So if the population of this substance, or the number of it, or whatever, keeps being cut in half, that means that my B is 1/2. It's like I'm multiplying by 1/2, which is the same thing as dividing by 2 over and over and over again, okay? And that takes 12 minutes. So because that's the time that it takes for B to happen, that is my P. So remember, peanut butter, B and P go together. How long will it take until there is 10% of the substance remaining? So how long will it take? T is my unknown. And we want to know when there's 10%, okay? So the problem with this question is that there's no start value or end value, right? It doesn't say that we started at 1,000 bacteria, find 10%. There's nothing, okay? But we do know that we're looking to end at 10% of the start value. So what we can do in situations like this is we can just pick a start value. And we want to pick something easy, okay? So I'm just going to pick a start value of 100. So that's a nice round, easy number, okay? Then we can determine 10% of that. So we're going to get 100 times 0.10, that 10%. So it's just going to be 10. So if we started with 100 radioactive substances, bacteria, whatever they are, 100 of them, 10% of them would be only 10 of them left. So we could do lots of different combinations. You get to just pick a value and then find whatever percent you're looking for. Okay, so now this is my A and this is my Y. So I'm going to plug that in. So I've got A, B to the T over P equals Y. So Y is 10, A is 100, B is 1/2, T is our unknown, and then P is 12 minutes. So if this one's in minutes, we know that T is also going to come out in minutes, okay, because this has to match that one. Okay, so again, just like the last one, we want to make just the power by itself. So to get rid of the 100, we're going to divide both sides by 100. So now we've got 10 divided by 100, so we get 0.1. And then the hundreds cancel, so then we're just left with the 1/2 to the T over 12. Okay, so 0.1, if we thought about that as a fraction, that is 10%. So we could have just gone straight to a 0.1, but I think this is a little bit more approachable and we kind of understand that more than just putting a 0.1 there, but that's what it turns out to be. So we know we've done that right. So now, again, we need to get this exponent where our variable is not in an exponent anymore. Okay, so we're going to log both sides. I'm going to draw my little guide to life, right? So I don't mess up what goes where. So this is going to be log. The base is 1/2, and you can write that as 0.5 if you want, of 0.1 is equal to T over 12. Okay, so what that means, and I'm going to just write this more as a true division, like fraction, kind of like that. Because if I want to get T by itself, I now want to multiply both sides by 12 to get rid of it. So T is equal to 12 times log of 0.5, like base 1, 0.5 of 0.1. So again, we just type this in the calculator, okay? So either you can do log using the boxes or log of 0.1 divided by log of 0.5. So that's that change of base formula. This one, like log of this one divided by log of this one. And we just use base 10 because that's what our calculator knows how to do quickest. You'd get the same answer either way. So when I do that, I get 12 times 3.32 blah, 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 blah. But I kept all my decimals. I multiplied that by 12, and I got 39.8 something that rounds up. So it's 39.9 minutes. So if this half-life was 12 minutes, that means 90% of it has died within basically 40 minutes. Okay, so that's really quick. We're going to do one last one, which is a little thicker. It's more graphical in interpretation. So the graph below shows how much medication is left in a patient's body after a number of hours after being administered. Okay, so I'm going to put my time in hours on my x-axis, and then my y-axis is the amount of medication, and I'm going to just assume that it's in milligrams. I don't actually know, but I like to just give it a unit, so we'll go with that. Okay, so what the first question asks is, what is the original dosage of medication? Okay, so right when time is 0, right when the clock starts, right when the patient was given the medicine, we can see that it was right at 100, and it kind of like blurs into that line. So it's a little tricky to see, but it is right at 100. This photocopied really weird. So at t equals 0, that's what we're looking for. The dosage was 100. And again, I'm just going to assume milligrams. Okay. How long does it take for half of the medication to be absorbed? So now we're looking for, okay, if we started at 100, 100 divided by 2 is 50 milligrams, right? We're looking for 50 milligrams left. And we can do that graphically by saying, okay, here's 50, there's this point, and so it kind of looks like right between the 1 and the 2 hour mark. Maybe a little bit bigger than 1, but it's hard to tell. So we're gonna say about 1 hour. It took about an hour for 50% of the medication to be absorbed. Okay. How long does it take until there's 5% of the medication left? Okay, so 5% of 100 is just 5 milligrams. And so if we look at that on our graph, it's halfway between 0 and 10. And we draw kind of a line over, there's that dot. That looks right about 4 hours. Okay, so this one was just interpreting that data off of a graph, so no calculations, but still an important skill to know how to do. Okay, so the biggest thing today was to know how to use that y equals ab to the t over p. These guys kind of go together, these guys kind of go together, and then how to solve for t. So it's basically an extension of the previous day's lesson. So there's more examples in the snap book, and then you guys have practice to do, and obviously let me know if you have any questions. Okay.